The German physicist Gustav Kirchhoff is credited with describing two of the fundamental laws describing currents and voltages in a circuit. In this video, we're going to discuss the first of these, Kirchhoff's current law. You'll recall that current is the flow of electrons. When electrons are moving, or when they're flowing through a conductor, you have current flowing. Current is measured in units of coulombs per second. Perhaps its most fundamental units would be charged particles per second, but because charged particles are so small, we typically talk about coulombs per second, or the name ampere is another unit that's typically used or associated with current. So coulombs per second and amperes means exactly the same thing. Simply stated, because charged particles cannot be destroyed nor created, the flow of current leaving a junction must equal the current entering, no more nor no less. So say we've got a conductor here and it comes to a place where there's a branching, and you've got, say, 5 amperes coming in here, 5 amps coming in, and we know that there is, say, 2 amps leaving in this branch. All Kirchhoff's current law is saying that if you've got 5 amps coming in, you've got to have a total of 5 amps leaving, or 2 amps here, so that would leave 3 amps in that branch there. Now you'll notice that current has both a magnitude, a number, a size, amperes or coulombs per second, but it also has a reference direction. When it comes to a point of junctioning, or a node as it's called, a junction or a node, currents need to be referenced. The direction that the current is flowing relative to the node needs to be referenced. This is 5 amps entering, this is 3 amps leaving, and 2 amps leaving. So in a mathematical way of stating it, we could say then that the sum of the currents, and by the way, you remember that we typically use the variable I to designate currents. The sum of the currents entering, or coming into the node, must equal the sum of the currents leaving, or going out of the node. In this case, the sum of the currents coming in, there's only one current coming in, so that would be 5, would equal the sum of the currents leaving, 3 plus 2 amps. Now, in analyzing circuits, we won't always know what currents are entering and which currents are leaving, or what the size of the currents are. In fact, it will frequently be our task to determine which currents are leaving and which are entering, and what is their measure, or in other words, how big is the current and which direction is it flowing. Generally speaking, it's going to be up to us to determine the size of the current and the direction of flow. And so to start, generally speaking, we're free to arbitrarily assign reference directions and name the currents. Here we have a node or a junction with 4 different branches, 4 different conductors being joined. Arbitrarily, we've assigned the current flowing in this branch here. We've defined it to be flowing in this direction. Now, we don't know. That'll be our job, is to determine whether it's flowing in or out. But we've just defined it as flowing in, and similarly the current here flowing in, whereas the currents in these 2 branches we've defined as leaving. It's totally arbitrary at this point. But having chosen this reference direction, we'll now stay with it. We won't switch our references midstream, so to speak. So we could then write Kirchhoff's current law by saying that the sum of the currents leaving, the sum of I out, must equal the sum of the I's in. In this case, those currents leaving are I2 and I3. The sum of the currents leaving must equal the sum of the currents entering, which again in this case is I1 plus I4. Another way of stating this Kirchhoff's law that may seem confusing at this point, but will make life a whole lot easier when we get into more complicated circuits, is to say that the sum of the currents leaving minus the sum of the currents entering must equal 0. And this is typically the way Kirchhoff's current law is stating, that the sum of the currents leaving a node must equal 0. The sum of the currents leaving the node must equal 0. Implicit in that statement is that some currents will be positive and some currents will be negative. Our convention is going to be that currents leaving the node will be given positive signs, and the currents entering the node will be given negative signs. Now, as I mentioned, this may seem just counterintuitive to some of you, but when we get into more advanced analysis techniques, it's going to be a whole lot easier and a whole lot easier to keep our signs straight if we use this convention. So really what we're saying is that the sum of the currents leaving the node must equal 0. Let's write that. That's typically how it's stated. The sum of currents leaving the node must equal 0. And as we've already pointed out, that implies that some of them are going to have to be negative, and our convention is that the currents leaving the node will be positive, the currents entering the node will be negative. It's something like house guests. When the house guests come, that's a negative thing. When the house guests finally get around to leaving, that's a positive thing. In this case here, then, we would say that the currents leaving I2 and I3, because they're leaving, they will have positive signs, I2 plus I3, minus the currents leaving, minus minus the currents entering, minus I1 minus I4 would equal 0. The currents leaving are given positive signs, the currents entering are given negative signs. Keep in mind at this point we don't know what the values of I1, I2, I3, and I4 are. Some of them may be positive, some of them may be negative. That's left for us to determine. So for example, if we knew that as the currents are referenced, that I1 equaled 6 amps, and I4 equaled 3 amps, and I2 equaled 4 amps, could we find the value of I3? Well, we have I1 leaving, or entering rather, I1 entering, it'll be a negative value. I4 entering, that would be a negative value. So we would have entering would be negative, let's start with the, as we've written it here, I2 would be 4 plus I3, which we don't know, so let's just go ahead and call it I3, minus I1, which is 6, minus I4, which is 3, equals 0. So we have negative 6 minus 3 is negative 9, plus 4 is negative 5, which we take to the other side. That tells us then that I3 would equal 5 amps. Now, let's see if that makes sense. I1 entering is 6 amps. I4 entering is 3 amps. So we've got 6 amps coming in. I2, we've been told, is 4 amps. So I've got 6 plus 3 is 9 amps coming in, 4 of them leaving, means that I3 then must contain the remaining 5 amps. Let's do a couple of more examples with a much more complicated circuit. Here we've got 1, 2, 3, 4, 5 different junctions or nodes referenced. Each one of these branches has a current specified, both the value of the current and the direction of its reference. So in this case, I1 is referenced leaving node 1 and entering I2. I2 is referenced leaving I2 and entering leaving node 2 and entering node 5. Similarly, I4 leaves node 3 and enters I5, and so on. So we could go ahead and write a KCL at node 1. Again, we're going to sum the currents leaving. which means that the currents entering will be negative, but the sum of the currents leaving must equal 0. So here we are at node 1. We have currents leaving. I1 is leaving, so that would be a positive. I1 is leaving. I3 is leaving, plus I3. And then still here at node 1, we have the current in this branch, which has been defined as I5, entering node 1. So I1 plus I3 minus I5 must equal 0. Similarly, let's sum the nodes at, or sum the currents leaving node 2, or write a KCL equation at node 2. Again, summing the currents leaving. I2 is defined as leaving. Notice that I1, which was leaving node 1, is defined entering node 2. So because it's entering node 2, we'll subtract it, because entering is a negative, just like house guests. So we have I2 leaving, I2 minus I1 minus this current right here, which we're told is 2 amps. So minus 2 amps. The sum of those currents must equal 0. Again, notice that because I1 is defined leaving the node 1, or leaving node number 1, when we're summing the currents at node 1, I1 has a positive sign in front of it because at this node it's leaving. On the other hand, when we're summing the currents associated with node 2, I1 is referenced into the node, therefore I1 has a minus sign in front of it. We're subtracting I1 at this point. Let's just point out that this convention is totally arbitrary. As I've noted, we're going to get to a point where this convention, although it may seem crazy to you right now, it's going to be very useful and it's going to be very helpful to keep track of signs when we get into more complicated circuits. You're free to choose whatever convention you want. Most of the world does it this way. Our class will be doing it this way, and just to make life easier on yourself, I'd encourage you to get used to this idea of currents leaving the node being positive or being added together, and subtracted from that are the currents referenced, are the currents entering the node, subtracting the currents referenced entering the node.